The title of the IWISH and the EMSS session is Healthcare General Application, and we have 4 speakers scheduled, but at now we have 3. So I thank you, of course, for your participation. I thank Caterina for the disponibility, for the availability, and so I introduce the first speaker, that is Gerald Zwettler. I hope to pronounce correctly your name. The title is EpiMon, Vision-Based Early Warning System for Monitoring Uprising Epileptic Seizure During Night. The number is 113. So if you're ready, you can start, please.
Protective words. Let's see if the sound is
fine. We can see your slides.
Welcome to our talk, EpiMon, Vision-Based Early Warning System for Monitoring Uprising Epileptic Seizures During Night. My name is Gerald Zwettler, and I've done this research work together with my colleagues from the research group Advanced Information Systems and Technology of the University of Applied Sciences, Upper Austria. The medical background regarding epilepsy. Epileptic strokes are a very severe medical seizure. The prevalence is around 0.5 to 1%, with a significant peak in age distribution between infancy and adolescence. There is a second peak when people get around 60 years of age. An incidence of around 40 to 70 per 100,000 residents leads to an overall 4% chance of getting affected by epilepsy during lifetime. And the consequences for health are really severe if there are no intermediate counteractions taken. Thus, there is a significant demand for automated monitoring systems. The tools available on the market, such as EpiCare or NightWatch, detect the change in a patient's heartbeat and muscle tonus. There are also audio systems like Lollipop or Hello Baby analyzing the infant's movement from the visual content. Nevertheless, many juvenile patients suffering from epilepsy do not show any changes in the heartbeat or in the muscle tonus. So none of the available systems on the market can thereby be utilized. The only chance to detect the uprising seizure is to detect the previous sign. This is a fine-grained visual implication. The patient thereby moves the eyes towards the affected region of the brain, and that can be detected in a visual manner, either by permanent observation during night by the caretaker, which is really a large burden for both the caretaker and the juvenile patient due to lack of any level of privacy. But our project idea thereby is to detect this previous sign in a fully automated way, utilizing computer vision. So the research questions we address is to develop a proof of concept prototype to detect the previous sign. Thereby, we have to analyze if state-of-the-art deep learning face detection is sufficient to be applied to night vision images too, without any further need for retraining or transfer learning. Furthermore, our conventional image processing concepts for pre-segmentation is suitable to allow for a bag of feature classification in a robust way. Material, we utilize images that are acquired with different cameras, either with a conventional baby phone and furthermore with the ELP state-of-the-art night vision camera system. Furthermore, we are using test sequences of 3 persons, 1 child and 2 adults in a different resolution and bit depth, also varying between portrait and landscape for individual testing. All of the testing series cover the images with either the eyes closed or opened, or the eyes or the face not visible due to occlusion by pillows or a blanket. Methodology, our system architecture you can find on the right illustration. There are 3 main tasks to handle, namely, first of all, the face detection and the pre-fragmentation. Besides the model calibration, to train it on the custom patient, and last but not least, the model comparison to classify the state of the eye, either the eyes being opened or closed. So for our hardware setup, we are using a Raspberry Pi in version 4 as the central processing unit and 2 ELP night vision cameras that are placed left and right of the patient to allow for an extended viewing frustum. The steering is controlled by a smartphone app, and we have some external alarm system and an emergency stop button to all of a sudden stop the alarm then. Face and eye detection is the first step to establish. We are using the MT-CNN. This can be applied to night vision images too. In a success case, this framework allows detection of the head area besides the eye and the nose position. But only a position for the eye does not allow any feature analysis. So we have further demand to get the region of the eye either closed or opened. And therefore we are using the graph segmentation to fragment the input images, which can be RGB, or in our case, night vision, similar to mosaic-like little regions. For these mosaic-like little regions, we are evaluating different features inside the region. All of these regions are modeled with a normal distribution, and we do that for a bag of features for the open eye and the closed eye model. Some of the features we utilized are listed below. The region size, is it a large region or a small one? The mean intensity inside the region, the relative region intensity relative to the entire face, the region intensity variability besides the circularity. These are the features to robustly detect opened and closed eyes. Besides, we have some geometric features as meter features, such as the vertical and the horizontal relative position. These two stabilize detection of the eye region prior to classifying the eye state. For classification of the eye state, we have our calibration phase where we train the opened and closed eye features. And based on these features, we are establishing and performing the comparison. We evaluate the probability density function. Probability density function is compared for some unknown frame where we don't know the eye state, and we compare the feature vector with the open and the closed eye model, and where there is the highest probability, the highest level of matching, we can conclude the final classification. Results, the features are pretty strong. You see on the right the relative brightness as well as the brightness variance. This gives a good discrimination regarding the histogram of the training model for open and closed eyes. So we are with this single features around 91%, 96% accuracy. And if you combine it with further features, you get higher level of accuracy. Yeah, the face detection is around 56 to 73% on single frame evaluation. This is a bit lower compared to the Microsoft face recognition tool, but can be further improved if the orientation of the face of the head is aligned prior to running these tools. The classification itself is pretty robust. With the babyphone data, we are around 94%. With the ELP camera, it's around 60%. Yeah, because there also the high quality night vision leads to some bright areas inside the face. So discussion and conclusion. There is some demand to improve the results regarding stability, mainly on the face detection. Position of the cameras is crucial. And for future usage, the custom trained models need to be features. What I've mentioned before, the modern camera systems are somehow too bright. So we need to find a way there to normalize the histogram, to balance the brightness level, or also to dampen the lighting emission, similar to a sunglass-like foil on the camera objective, to focus on the bright, opened eyes at night. Thank you for your attention, and many thanks to the Austrian Research Promotion Agency, FFG, for allowing us to work on this highly relevant medical topic. Thanks.
Thank you, Gerald. Very nice presentation, very interesting.
Everybody. My name is Gerald Zwettler.
Sorry. Yeah. And I ask kindly to put off your screen sharing. Fine. And I ask the audience if there is any questions to Gerald for his experience. I break the glaze. So, do you have any? I mean, you said that in about the problems are the camera capacity to well define the eyes situation. So, what in which way you think to ameliorate the situation, the actual situation?
Well, with the old cameras, it was not a problem because there the quality was really low. So only the eyes themselves were bright, shining. But with the modern cameras, you get so much light in the room that all of the face is somehow reflective, like in a real world scenario with reflections. So we have to dampen that. We haven't had time to look into that in depth by now, but we will focus on that the next half year of development within that. Because the premise of our work, the idea is always that, as we know from wild animal cameras used outside, that at night opened eyes glare, which is true also for modern cameras, but we need to dampen the reflections, the lighting all around the face.
Yes, thank you. And I think that, I mean, the subject that is monitored has to collaborate in such a way.
Sorry?
I mean the epileptic patient.
Yeah.
When is monitored, has to collaborate in some way or not?
Yeah, there is still an observer, but the observer is outside the room. So only monitoring on a smartphone. And if the eyes are opened or not visible, you get a soft alert at first. Then you can check the room if everything is fine. So instead of being inside the room together with the juvenile patient, you can monitor it from outside, check the video live feed if everything is fine, or getting the automated alert if the eyes are open. And if you're awake at night staring, this is a really good sign for an uprising seizure.
Right. Thank you, Gerald. Very nice. And are there any questions, more questions from the audience? Well, if no, I thank you again. And we carry on to the next presentation, to the next work. That is postural evaluation and symptom acquisition based on IoT-driven multisensory fusion. Number is 144, and the speaker is Klinger.
Yes, of course. One moment, I have to share the screen and
take your time.
Sound. Correct. And I hope now.
Yes, we see your screen.
Okay. And I hope it is correct, though. Nice. So I can start. So at first, thank you for the friendly introduction. And I think it is necessary to say thank you for making this online conference possible. So what is the topic? Let's have a short look at the agenda. We have a short introduction, and then we will have a short idea about the background of the project and about the system architecture, because this system architecture is used sometimes now for different projects. And so we will have a short application overview, and of course we have an introduction to this application, which is the focus here today. And after this, we will have a topic, it's called data fusion, and then we will have a short conclusion and further work, some words about. So what is the idea? The idea is upcoming, so the background from an ENG, so electroneurogram-based control of prosthesis. And in this project environment, we have developed the necessary hardware and software to put the control of prosthesis on a new basis. You can see here above the measurement component with the signal pre-processing and the connection of the corresponding systems for control, monitoring, and configuration. It proved necessary in this project to extend the measurement modules to include motion detection, which is solved by adding IoT, so Internet of Things sensors. See below in short a very, very small example. The reason for this motion detection was the problem of zero space movements, which we encounter again in today's presentation. So what is the idea of this IoT system? Let's have a look at the IoT system. So the use of our in-house developed IoT modules has been facilitated by the establishment of a platform paradigm, which, due to its scalability, has simplified the design and development of further modules. You can see here the 4 essential components of an IoT module that need to be rescaled with regard to size or capability in each project to get appropriate customization. It is important to use core modules that reduce the development effort of new modules. Of course, in most cases, we are using an ESP32 for this objective. And so it is very, very easy to use this module because of its capabilities, for example, in the area of communication. By the way, a short statement at this point, because in Europe, we have neglected the development and production of integrated hardware for decades. And we have hardly any knowledge of technologies and have thus placed ourselves in a position of great dependence. The daily reports about delivery bottlenecks from ASICs make this more than clear nowadays. So sometimes, you know, a cup of coffee costs a half of such an ESP32 module. And sometimes I think it is very, very interesting to think about. And of course, hardware and software are both, I think, interesting, or better said, key skills to have a chance in the future technologies. So, but after this idea, what is the system architecture here? So the architecture of all these systems is always built in the following way, even in the project presented here. On the left, you see the IoT module, for example, with different front-end modules with different sensors. Then a gateway represented here by a smart device. In the beginning of the project, we are often use Raspberry Pis for this gateway functionality because sometimes it is easier to use this Linux-based system than, for example, using iOS or Android systems. On the right, you see the corresponding backend, which provides servers, services, database, and of course, necessary methods and algorithms. In the project here, again, I say it is a ESP32 based module, and this module sends the information to the gateway using, for example, a standard protocol, and we have used the MQTT protocol, which is a very good choice, I think, for all this IoT stuff. So let's have a look using this project architecture. It is used, for example, in the past for the last project, so distributed measurement of colon dioxide in the context of the pandemic. You can see here an example, a curve, for example, of colon dioxide, the concentration in a room, and, for example, the positioning on flexible modules. And we are thinking about now using these modules also in the future to use the information for example, an appropriate room ventilation. But what is the project focus here? Of course, we have a running project with gate control. And in this context, the Medical University in Innova has a request for us to say, okay, we have an everyday problem. So there is not, I think it is a link to the pandemic, but more a secondary one. But due to all these all-day use of video conferencing, so the corresponding posture in front of the screen can often be improved. We have thought about, I said, gait analysis before to improve prevention, health maintenance, and rehabilitation approaches. So these considerations have been taken up again for this project in order to improve the posture when using video conferencing. So these different postures are all represented using the software from Unity, because we have found it very practical in this environment because of the given features of, for example, humanoid models. So it is very, very easy. You can see it here. You can see here the very, very easy idea of what is a good seating, for example, and on the right you see, okay, this is the idea. It is rather a poor posture on the right. For example, you have some bending and all this stuff you can, I think, impress on your own. What is, for example, a poor posture here? So one problem we had, because one problem was because of this idea how many sensors we have to use. So in order to have as few sensors as possible, we have developed, we call it a T model, which is an abstraction of a humanoid in a sitting position. The advantage is the abstraction of the spine, which consists, of many joints and vertebrae, and those concrete individual participants can hardly be captured by reasonable effort. A sensor in the shoulder, for example, can now be transformed into a corresponding posture by the T model. The prerequisite, however, is that the position of the buttocks is stationary. So here, for example, you can see on the next slide, in yellow, the joints we model for the T model. For the prototype, for example, we use MATLAB. And so we can now say, okay, we can rotate or bend in 1 or 2 dimensions here. So let's have a short look at this MATLAB. Here in MATLAB, the T model looks like this from the front or top. So you see it is very, very simple. And in the next slide, for example, you have here a bending to the front left shown in this model. But of course, I have said it at the beginning of the presentation, we have a small problem, because this already mentioned problem of zero space motion. From an initial position shown on the left here, various movements are performed until the person returns to the original posture. However, this final posture differs from the original posture because with the help of inverse kinematics based on the sensor data of the sensor, it cannot be decided unambiguously with rotational joint, shoulder, or lumbar spine. So we can deal with this problem by using several sensors shown here, yes, of course, but another sensor is mounted here on the lumbar spine. I can show you, for example, there's also one moment, you see on the right, I'm not sure, you have no chance, I have at the moment no pointing device, but you can see here on the right that there is a change in the angular of the lower spine component. So we can now do the following. For example, we can add several sensors shown here. Another sensor is mounted on the lumbar spine. You see it, and in addition, sensors are already mounted, which can be used for the gait analysis. But we need then something. We need then data fusion. So data fusion is necessary to overlay the single information of these sensors. But let's go one step back. What is, for example, a simple system in this context? A simple system provides a periodic reminder. It no measurement or monitoring of specific parameters. So prevents a long-lasting current position. I think it is something like an app. So I think there is no sensor necessary, and of course, no data fusion required. But of course, there is no certain idea about your posture. It is only a reminder. And on the other hand, there is a possibility of an analytic system with monitoring of motion data, where we have, for example, a model-based identification of different, let me call it, unhealthy positions. And for example, maybe there's a chance to just suggest, for example, some movement for a specific relaxation of specific muscle groups with regard to the unhealthy position before. But of course, there is a model required. And of course, there's data fusion required. So because this data fusion is something, a cognitive tool, for example, for situation awareness. So the question is, what are now the right idea to do? I think we need an analytic system, but of course there are some problems in focus, and I think we have to concentrate on. So, okay, data fusion, I think it is well known what is the background. So we have multiple sensors. For example, the idea is we want to obtain the truth. So the question is, we have seen before, what's about this idea of unambiguously situation during the posture. So we have to combine data. We have to the idea of what sensors are doing, so in a manner of competitive, complementary or cooperative information of the different sensors. Of course, we then can generate a knowledge map, and with regard to the posture, what is a good posture, what is a bad posture, of course, but you see here we have another problem, because what is a good posture in total? So an absolute good posture, we need something to calibrate. So, okay. All these data fusion characteristics, I think, are well known. And at the end, there is one point, what's about the verification, of course. So only to say something about data fusion. So I think it's very, very interesting to have an idea about the difference between the data layers, of course, and the information layers. And for example, and such a cognition here is worked out between this idea of the layer of data and the layer of information. And in addition, the circumstance is considered abstractly which way the information flow between people and situations here take place. So let's have another point we have to focus on. Speaking about data fusion, I think we speak about models, because a model is, for example, an idea of relation in between a system. So data fusion and modeling, and of course, which models the relationship between these inputs and outputs of the system, shown in the upper left or in a mathematical manner in the upper right, have some, or better said, a lot of affinities. So a model helps to understand the relationships between individual sensors, and of course, it'll be able to process them together accordingly. A model is therefore a valuable aid in data fusion, of course. And the data fusion can also be done accordingly only on the basis of the knowledge of system interrelationships. In our use case, the question arises as, for example, how we proceed with this model building. So what we are doing at the moment is the following. We have a concept here developed in the last years. It is called the Symbiotic Cycle, and the Symbiotic Cycle now makes a relation between the data fusion and the model generation. So this Symbiotic Cycle is based on 5 modules. For example, you have the actual process, of course, so you have to interconnect to this process. You have to have a simulator. For example, we have MATLAB here at the moment, but of course, sometimes you need a digital simulator written on your own because of specific ideas behind and specific synchronization effects. And we need, of course, some verification. In our project, this is a very, very interesting point because we have all the time the question, what is a good posture? So the verification has to be done by the person, which is now, for example, in the focus of the system. So it is a good question if this verification is the right one to say, okay, this is now a good or a bad posture. Because you know yourself, sometimes you're very relaxed, but of course, maybe the posture is not the right one, whatever right means. So, and we need another thing, the machine learning, which builds a process model and modifies it according to the cycle. And what is interesting, the most important point here is of this symbiotic cycle, that there's an interrelation within these 5 modules. So the symbiotic cycle makes through the simulator, steers the process to where the model is very inaccurate. For example, if you have all the time the same input values and you have the same output values, and it is very, very difficult to depend some changes and interrelations between inputs and outputs. So you have to bring your model in a certain situation to see, okay, there is an influence from input A to output A or not. So there is a need to improve the model, and so this does not work for all projects. This is a problem. For example, we have had in the past a small project with a truck with a trailer, and the focus was the wheel bearing of this trailer. And so the idea of this symbiotic cycle tells only the driver, hey, we have to have a very, very extreme curve now because we want to know what is about the wheel bearing in this situation. And you see, okay, in the normal traffic, it is not possible with such a trailer to say, okay, I have to go right or left in a certain manner. In our application, I think it is much easier to say from the symbiotic cycle to the person what it has to do. And then you have a chance, including the model, starting with the T model, for example, to say, okay, what is now the influence of sensor A? What is the influence in sensor B? And then you have, for example, after modeling this relation, you have then the chance to say, okay, what is reachable with 1 and what is reachable with 2 sensors, for example, with regard to whatever it means, a good posture. So let me come to the conclusion. So this IoT-based framework we have now has a wide range of applications. And of course, we all use the same architecture. Sometimes we have different models, different modules in between the IoT system and between the gateway. But of course, the architecture will work very well. So the modular structure of this platform simplifies the utilization, okay, of course, in different contexts. So the continuous data recording is for us the key to an improved knowledge of all processes. And of course, in most cases, we have no data about all this stuff. So sensor fusion is a key factor. It seems to be in this project the key factor, for example, to say, okay, we have an analytic model to say something about the posture. And so we have a chance, for example, to have a better evaluation and awareness of a certain situation. And of course, again, hardware and software, even in this project, are essential skills. And of course, the integration in the system of both hardware and software domains they say something about the success of the project. What is the further work, of course? Yes, the symbiotic cycle is under development at the moment for this project because we have to change some things because of the data input and output context. And of course, we want to provide now the app for the symbiotic cycle and for the verification reasons. You know, the user then has to say something about his own posture. And of course, there's one point very, very important with regard to the past. We have to implement better quality gates because between an idea, a concept, a prototype, a product, there are different constraints and different requirements. And sometimes we go too far, for example, at one point. For example, if we have only to develop a prototype, this is something we have to do on our own here. If, for example, implementing, as I call you, the quality gates. So 2 examples for the future work. The one is an idea in the future to have, for example, some platform for the data fusion where you have a lot of inputs and maybe there's a chance to detect interference between different aspects. For example, if you have a look back at the pandemic situation for the measurement of carbon dioxide concentration, you have an idea about temperature, about humidity, about, for example, carbon dioxide, and maybe you have some data in future and you have a chance to understand what is about the infections rate here. And the second one is only a short example. We have to think about if you have a product and we are thinking about this product idea with regard to the posture situation here, then we have to implement the plug-and-play extension for the different sensors. And so we are working, for example, on these ideas how we can realize this plug-and-play feature. Okay, we will see next year, or I'm sitting in a better way here in the chair, if there is a chance of an attendance to the conference. Thank you very much. I hope you have some questions.
Thank you, Klinger. Very nice and extended presentation. If there are any questions, can you put off your sharing screen? Thank you very much. Are any questions coming from the audience? So, which is your idea about the first application in your mind of this system?
Oh, the first application is a small box, including the sensor, for example, with a SD card, for example, managing the raw data and the connection, for example, channel to a smartphone. And then you have a chance, for example, to adapt this sensor to the smartphone. You bend it on your shoulder, for example. Then there is a small process about calibration. So there are some, let me call it exercises you have to do with your system. And then, for example, the system says, okay, you can start. And then it is monitoring what is happening with your position. And then it gives you some information, for example, about the time, for example, you're in a certain position. And then there are some ideas about what the system tells you, what you have to do, for example, with regard to some relaxation of certain muscle groups and so on.
Right, thank you very much. Any other?
Yes, I wonder, is it possible to replace to use all the smartphones instead of sensors, because so that everyone will be able to take a few old smartphones he has at home and stick it to his positions and use them in place of sensor? And also, is it open source software?
Of course, I think it is possible to use a smartphone, yes. The only problem is the size of the smartphone. And for example, if you have to connect the sensor at your lumbar spine, yes, then a smartphone, I think, is not the best idea, huh? What do you think?
It would just be so that people would be able to use it just trying to see if it works or not for them, and then if it works, maybe they buy the right product. I don't know.
Okay,
But
I think
so that
at the first point we have a release, I think, on you, okay?
Sorry, what did you say?
Sorry, if you have a first release, we are say, okay, it is a good one, I think, on you, okay?
Okay, thank you.
Right, thank you to everybody for this nice discussion. I ask, nobody is present for the last one, Dario Panada of Vision Parsia, isn't it?
Not, but we have a video.
Yes, but sorry, Caterina, yesterday the committee, the organization committee said that no people, no presentation.
Ah, okay.
So I have to follow this indication.
Okay.
I think it's correct anyway. So, if I will see, we have finished our session. Healthcare general application is now concluded, and I have to thank a lot the speakers, Gerald Zwettler, Jonas Schur, and Volkhard Klinger. So thank you, my compliments, and see you next year in Rome in presence, of course. It's not a dream, but is the IWISH conclusion thinking. So thank you again, and see you next year. Bye-bye.
Thank you, bye-bye.
Thank you, bye.
Bye-bye.
Thank you. Bye.
Grazie Caterina. Ciao.
Bye.
Bye-bye.
Bye. See you next year in Rome. Bye.